Welcome to the session on half-range Fourier integral representations. In the previous class, we discussed the Fourier integral representation of a given function. If f of t is satisfying the Dirichlet conditions and integral from minus infinity to infinity modulus of f of t dt is less than infinity, then we can represent the given function f of t as an integral. F of t is equal to integral from 0 to infinity a omega into cos omega t plus b omega into sin omega t d omega, where a omega is given by a omega is equal to 1 by pi into integral from minus infinity to infinity f of t into cos omega t dt, and b omega is given by b omega is equal to 1 by pi into integral from minus infinity to infinity f of t into sin omega t dt. We can represent the function f of t like this integral at all points t where f of t is continuous. If there are some points of discontinuities, then the value of the right hand side integral can be obtained by taking the average of the right hand limit and left hand limit of the corresponding points of discontinuities. This is the Fourier integral representation of a function. Clearly, from the conditions specified for the Fourier integral theorem, this integral representation exists only when the function is defined for all values of t, that is, function is defined in the interval minus infinity and infinity. If the function is defined in half range interval 0 infinity, we can find the two representations of a given function. First one is the Fourier cosine integral representation, and second one is the Fourier sine integral representations. These are known as the half-range series representation, the half-range Fourier integral representations of the given function. Note that if f of t is defined in the interval minus infinity and infinity, then there exists a unique integral representation, unique Fourier integral representation. If f of t is even, then the unique representation will become a cosine integral representation, and if f of t is an odd function, then the unique integral representation will become the Fourier sine integral representation. But if f of t is defined in the interval 0 to infinity, that is, f of t is defined in the half range interval 0 infinity, then we can find two integral representations for the function f of t. First one is the Fourier cosine integral representation, and the second one is the Fourier sine integral representation. The definitions are: the Fourier cosine integral representation of a function f of t defined in the interval 0 and infinity is f of t is equal to integral from 0 to infinity a omega into cos omega t d omega, where a omega is given by a omega is equal to 2 by pi into integral from 0 to infinity f of t into cos omega t dt. Here, this integral representation exists for all points of t where f of t is continuous, and at a point of discontinuity, the value of this right hand side integral is obtained by taking the average of the right hand limit and left hand limit at the point t where t is a point of discontinuity. This is the Fourier cosine representation, that is half range cosine representation. And the half range sine integral representation is given by f of t equal to integral from 0 to infinity b of omega into sine omega t d omega, where b omega is given by b omega is equal to 2 by pi into integral from 0 to infinity f of t into sine omega t dt. This integral representation exists for all values of t where t is a point of continuity. At the point at any point of at a point of discontinuity, the value of this right hand side integral is obtained by taking the averages of left hand limit and right hand limit. This is the Fourier half range Fourier sine integral representation. Now, we have to work out some example problems. First one is, find a Fourier cosine and a Fourier sine integral representation of the function defined by f of t is equal to cos t for 0 less than or equal to t less than or equal to pi by 2. And f of t equal to 0 for all t greater than pi by 2. Clearly, this function is defined in the interval 0 to infinity, that is f of t is defined in the half range interval 0 to infinity. Therefore, we can find two integral representations. First one is the Fourier cosine integral representation, and the second is Fourier sine integral representation. Both represent the same function f of t. We have the Fourier cosine integral representation is f of t is equal to integral from 0 to infinity a omega into cos omega t dt, d omega, where a omega is given by 2 by pi into integral from 0 to infinity f of t into cos omega t dt. This is the Fourier cosine integral representation. And the Fourier sine integral representation is f of t is equal to integral from 0 to infinity b of omega into sine omega t d omega, where b omega is given by 2 by pi into integral from 0 to infinity f of t into sine omega t dt. These are the definitions. Therefore, first of all, we have to find this a omega for the cosine integral representations. that is a omega is equal to 2 by pi into integral from 0 to infinity. Here the function is defined in two ranges. One is from 0 to pi by 2 and then from pi by 2 to infinity. Therefore, we can split this limit of integration 0 to infinity into two limits. First one is 0 to pi by 2 and then pi by 2 to infinity. Therefore, this is equal to that is a omega equal to 2 by pi into integral from 0 to pi by 2 f of t into cos omega t dt plus integral from pi by 2 to infinity f of t into cos omega t dt, which is equal to 2 by pi into, here the function is defined as 0. For t greater than pi by 2 means t is from pi by 2 to 0, in which case the function is defined as 0. Therefore, the second integral will become 0 and a omega equal to 2 by pi into integral from 0 to pi by 2. In this case, the function is defined as cos t. Therefore, a omega equal to 2 by pi into integral from 0 to pi by 2 cos t into cos omega t dt. That is equal to, here this is of the form 2 cos A cos B, which is therefore, this is equal to 2 by pi into integral from 0 to pi by 2. Here it is 1 by 2 into cos t plus omega t plus cos t minus omega t dt. Two cos A cos B is cos A plus B plus cos A minus B. Therefore, this is equal to integral from 0 to pi by 2 1 by 2 into cos t plus omega t plus cos t minus omega t dt. That is here 2 and 2 cancelled. This is equal to 1 by pi into integral from 0 to pi by 2 cos, here we can write cosine of 1 plus omega into t plus this is cosine of 1 minus omega into t dt, because the integration is with respect to t. Therefore, we write this angle like this here 1 plus omega into t, and in this case we write 1 minus omega into t. One integration we get this is equal to 1 by pi into integral cos 1 plus omega t dt is sine 1 plus omega t divided by 1 plus omega plus here integral of cos 1 minus omega into t is sine 1 minus omega into t divided by 1 minus omega between the limits 0 and pi by 2. This is equal to 1 by pi into, when we applying the upper limit we get sine 1 plus omega pi by 2 divided by 1 plus omega plus sine 1 minus omega into pi by 2 sine 1 minus omega pi by 2 divided by 1 minus omega minus when we apply the lower limits we get sine 0 by 1 plus omega, that is 0, and the second term will become also 0 also, because sine 0 is 0. this is equal to 1 by pi into, here we can write sine 1 plus omega into pi by 2 means sine of pi by 2 plus omega pi by 2 divided by 1 plus omega plus sine, here 1 minus omega into pi by 2 means sine pi by 2 minus omega pi by 2 divided by 1 minus omega. That is equal to, here we can write this as sine 90 plus theta. Sine 90 plus theta means cos theta. Therefore, this is equal to 1 by pi into, here cos omega pi by 2 divided by 1 plus omega here also sine 90 minus theta means cos theta. Therefore, this also in the numerator it is cos omega pi by 2 divided by 1 minus omega. That is equal to 1 by pi into, in the denominator we can write 1 plus omega into 1 minus omega, that means 1 minus omega square. Here 1 into cos omega pi by 2 is cos omega pi by 2 minus omega into cos omega pi by 2 plus 1 into cos omega pi by 2, that is cos omega pi by 2 plus omega into cos omega pi by 2. That is in the numerator here minus omega cos omega pi by 2 and here plus omega cos omega pi by 2, which will be cancelled, and the remaining is cos omega pi by 2 plus cos omega pi by 2 means 2 times cos omega pi by 2. Therefore, A omega equal to two times cos omega pi by 2. 1 by pi is common, 1 by pi into 2 times cos omega pi by 2 divided by 1 minus omega square. This is the value of A omega. Therefore, the Fourier cosine integral representation of this function is given by f of t is equal to, we can write f of t as integral from 0 to infinity A omega into cos omega t d omega. A omega is this, that is 2 by pi into, this 2 by pi can be taken outside of the integral. Therefore, f of t equal to 2 by pi into integral from 0 to infinity cos omega pi by 2. Here omega pi by 2 is the angle, divided by 1 minus omega square into cos omega t d omega. This is the Fourier cosine integral representation or half range cosine representation, cosine integral representation of this function. Now, we have to find the Fourier sine integral representation of this same function. By the definition, it is f of t equal to integral from 0 to infinity b omega into sin omega t d omega, where b omega is given by 2 by pi into integral from 0 to infinity f of t into sin omega t dt. Therefore, b omega equal to 2 by pi into integral from 0 to infinity. This total range can be split into two intervals. First one is from 0 to pi by 2 and then pi by 2 to infinity. Therefore, we can write b omega equal to 2 by pi into integral from 0 to pi by 2 f of t into sin omega t dt plus integral from pi by 2 to infinity f of t into sin omega t dt. In this case, function is defined as 0. Therefore, the second integral will become 0 and the remaining is b omega equal to 2 by pi into integral from 0 to pi by 2. Here f of t is defined as, from 0 to pi by 2, f of t is defined as cos t. Therefore, cos t into sin omega t dt. Which is equal to 2 by pi into integral from 0 to pi by 2. Here we can write this is of the form 2 cos A sin B, which is sin A plus B minus sin A minus B. Therefore, we can write sin t plus omega t minus sin t minus omega t all divided by 2 dt, which is equal to 2 by pi into, here 2 and 2 cancelled, and therefore this is equal to 1 by pi into integral from 0 to pi by 2, here the upper limit is pi by 2, sin, we can write this as t plus omega t means 1 plus omega into t minus sin, here we can write 1 minus omega into t dt. On integration, we get this equal to 1 by pi into integral sin 1 plus omega t dt means minus cos 1 plus omega t divided by 1 plus omega minus, here integral sin 1 minus omega t dt means minus cos, therefore this will become plus cos 1 minus omega t divided by 1 minus omega between the limits 0 and pi by 2. That is equal to 1 by pi into, on applying the upper limit, we can write this as minus cos 1 plus omega into pi by 2 divided by 1 plus omega plus cos 1 minus omega into pi by 2 divided by 1 minus omega minus, when we apply the lower limit 0, we get cos 0 by 1 plus omega. Cos 0 is 1, therefore we get minus 1 divided by 1 plus omega plus, here cos 0 means 1 divided by 1 minus omega. This is equal to, we can write this as 1 by pi into, here minus cos, we can write this angle as pi by 2 plus omega pi by 2 divided by 1 plus omega plus, here cos pi by 2 minus omega pi by 2 divided by 1 minus omega. This is minus, here we can write 1 by 1 minus omega minus 1 by 1 plus omega. Which is equal to, here minus cos 90 plus theta. Minus cos 90 plus theta means sin theta. Therefore, we can write this as 1 by pi into, this is sin theta, means here theta is omega pi by 2, sin omega pi by 2 divided by 1 plus omega. Here cos 90 minus theta, it is sin theta. Therefore, we can write plus sin omega pi by 2 divided by 1 minus omega, minus, here we can write 1 minus omega into 1 plus omega in the denominator, that is 1 minus omega square. Here 1 plus omega into 1 is 1 plus omega. In the numerator it is 1 plus omega into 1 minus 1 minus omega. That is here this is 1 minus 1 is 0. Omega minus minus omega means omega plus omega, that is 2 omega. In the numerator it is 2 omega. Now, on simplification we get this is equal to 2 by pi into sin pi omega by 2, or sin omega pi by 2 minus omega all divided by 1 minus omega square. This is the value of b omega, and therefore, the required Fourier sine integral representation of the given function is f of t equal to integral from 0 to infinity. B omega is 2 by pi. Therefore, this 2 by pi can be taken outside of the integral into sin omega pi by 2 minus omega all divided by 1 minus omega square into sin omega t d omega. This is the required Fourier sine integral representation of this given function. We got the cosine integral as f of t equal to, this is the sine integral, and cosine integral is f of t equal to 2 by pi into integral from 0 to infinity cos omega pi by 2 divided by 1 minus omega square into cos omega t d omega. Both the two representations will represent the same function f of t equal to cos t for 0 less than or equal to t less than or equal to pi by 2, and f of t equal to 0 for t greater than pi by 2. Here the function is defined in the half range interval 0 to infinity. Therefore, we obtained the two representations for the same function. With this example, I would like to conclude this session. I hope that all of you have understood the Fourier sine and Fourier cosine integral representations. Thank you for watching this class. Have a nice day.